In this video here, looking at something in chemistry we call the mole. So before we get there, something to think about. So if I asked you, 1 dozen donuts is how many donuts? Well, most of you would say, well, that's 12. Promise this all comes together at the end. Just bear with me here. If I asked you, well, how much does 1 dozen donuts weigh? And you could probably give me a pound. So let's say they weigh, let's say they're a half a pound. Well, that's about, actually, let's say they weigh 1 pound. So that's a half a kilogram. And if I asked you, well, how much space would those dozen donuts take up? And we measure space. In a chemistry class, we'd measure it in liters. And here, I'd say if you weighed them end to end, I don't know, maybe, kind of 2, maybe 3 pop bottle, 3 liters long. So we'll just call it 3 liters for what we're doing here. So just different ways of measuring donuts. So we can measure by how many, how much they weigh, or how much space they take up. So like I said, my point, we can measure these in a number of different ways. But the nice thing about this is it allows us a convenient way for converting. So if I said I have 1 kilogram of donuts, well, how many dozen is that? Well, based off of that previous, we said, 1 dozen is a half a kilogram. So if I have twice as much, I have 2 dozen. Well, how many donuts is that? That's 24 donuts. So we kind of get this relationship. We can go between how many to the volume to the mass. We can use those relationships. And big here. So this works the exact same in chemistry. The only difference is our items, they're really small. We're talking about atoms. We're talking about molecules. We're talking about ionic molecules, which we call formula units. So we're talking in much, much, much smaller entities, smaller pieces, rather than a donut, which is very tangible. So how do we measure stuff? In science class, again, we measure mass in grams. We measure length in either the meter or the centimeter, or all those other prefixes. And volume, usually we measure it in milliliter. That's what all of our graduated cylinders and stuff are based on. Or centimeter cubed, which is the same. So these two things, if I had 1 milliliter, that's 1 centimeter cubed, that's 1 cc. They're all the same thing. And then I guess the other way of measuring things is, well, we can measure amounts of things. And just like we say a dozen is 12, in chemistry we just can't say, well, we can say I have a dozen atoms, but that doesn't mean a whole lot because these things are so small that a dozen atoms, that's really no different than saying I have 1. You can't see that, you can't touch that, you can't feel that. So to measure the amount or the number of particles, we use something called the mole. And you'll see that abbreviated MOL because 4 letters is too long, I guess, I don't know. But a mole is just a number, think a dozen. A dozen is 12. A mole is just a number as well, and I'll show you that number here in a second. But it is a number used to count small particles. So again, dozen means 12. You know that definition in your head. A mole is 6.022 times 10 to the 23rd. That's a number you might as well just start ingraining in your head now. We will use this, or you will use this in chemistry from now until whenever you stop taking chemistry. So 6.022 times 10 to the 23rd. Yes, we have scientific notation again. We didn't do all that work at the beginning of the year for nothing. This is why, another reason why we did it. This number is also called Avogadro's number. You may remember seeing the sign on my door of the weird looking guy that said, "Hey ladies, take a number." That was Amedeo Avogadro, and that number should look familiar to you. That was his number. But we use such a big number, so this is 6 with 23 zeros after it. You know, we're talking billions of billions, or actually more than that even, billions of millions. So we use such a big number for convenience because it makes these small things tangible. I'll show you an example in class, but I can show you what this many particles of water looks like. I can show you what this many particles of sucrose, you know, C12H22O2, of every chemical we have. I can show you a mole, and it's something you can see. It's something you can hold. Whereas if I said I have a dozen atoms of carbon, you're not going to be able to see that. So we do this for convenience because it makes them big enough amounts that we can see them. This mole, you know, just like a dozen, we can kind of make conversions between. This mole is equal to a couple of things just like that. It is equal to Avogadro's number, so it's equal to this many particles. It's also equal to this much volume. So 22.4 liters of any gas, be careful there, it has to be a gas, at STP, where STP is standard temperature and pressure, which anytime I give you or ask for a volume, it's going to be at STP. We don't have formulas yet, which is something we'll get to second semester for converting, well, what if it's not at STP? But for right now, just know that standard temperature and pressure is 1 atmosphere and 0 degrees Celsius. This just gives gives scientists a way for, you know, all measuring the same thing. Like, given these conditions, this is how much it is. Because if you change those conditions, like temperature or pressure, volumes are going to change. So they had to define something, and that's what this is. And then the third one, 1 mole was also equal to mass, and it's equal to the atomic mass in grams. So, which we call molar mass. So there's a definition. Make sure you know what that definition is. It's the mass of 1 mole of a compound. And our units here, grams per mole. So again, you know, thinking conversions, you know, thinking kind of ahead a little bit. We have complex units. We have grams up top, moles on the bottom. But what this means is, if I have, let's say this, we gave you water earlier. We mentioned water earlier. Well, water is 2 hydrogens, so hydrogen, and we said 2 of them. If I look at the periodic table, hydrogen's atomic mass, so the number on the bottom, 1.01, and times 2, plus oxygen's atomic mass, which is 16.00. Add those together. Water, H2O, has a molar mass of 18.02 grams per mole. Sorry for the writing here. But what that means is 1 mole of water weighs this much. So this much weight per 1 mole. And now I can go weigh that on the scale and say, okay, here's a mole of water. I could then, you know, I could convert that mole to particles of water. So how many H2O molecules are in there? I could also, now it's not a gas, so I can't use that. But we can use these relationships based off of these things to convert between each. So that's the idea of the mole. Anytime we say mole, think dozen. So a mole is just an amount. Yes, it has a weird name, but it's just an amount.